Schofield, Wisconsin, Middle America. If you find yourself here in winter, you'll experience the real cold of the Midwest, freezing air that cuts to the bone, and endless snow. But inside the massive plant floor at Merrill Iron and Steel, the atmosphere is completely different. It smells like ozone, molten metal, and machine oil. Right here, 1,500 miles from the gaming tables of Nevada, the skeleton of what would later be called the Death Star was born. Allegiant Stadium in Las Vegas. Our introduction doesn't start with blueprints, but with scales that don't fit inside your head. The star of this stage? The box girder. Forget ordinary rails or channel beams. The roof beams for Allegiant Stadium are hollow steel structures with a rectangular cross-section, so massive that an adult could comfortably walk upright inside each one. Each section weighs between 60 and 80 tons. This isn't just a hunk of iron, it's complex engineering geometry with internal stiffening ribs, partitions, and attachment nodes for cables. When you stand next to one of these beams, you feel like an ant beside a spaceship. The steel here is thick, black, and impossibly cold to the touch until a torch meets it. Every millimeter of welded seam undergoes ultrasonic testing. Not a single void or crack gets to exist because these beams will support a roof worth hundreds of millions of dollars. Since the beam is hollow, the welder often has to work inside the box. Picture a person in a cramped steel echo chamber where every hammer strike or hiss of the arc is amplified tenfold. The air is thick with sparks and the walls radiate a dry, searing heat. The real magic happens during submerged arc welding. A massive welding head moves slowly over the joint between two thick plates. It doesn't just spark, it pours a layer of gray powder onto the seam. Right beneath that powder, hidden from sight, an electric arc burns. You don't see the blinding flash, only hear a low rumble and watch as a perfectly even seam, glowing red hot, appears on the other side. The flux melts, forming a glassy crust that shields the metal from oxygen. A particular challenge is the multi-pass approach. Because the beam walls at Allegiant Stadium are several inches thick, a single weld takes 20 or 30 passes. A robot or master welder builds up the steel meat layer by layer until two separate sheets become a monolith. When the beam is ready, its welds flash silver against the black factory steel, and an ultrasonic scanner confirms. This steel skeleton will support the weight of an entire skyscraper. To give you a sense of scale, one such section weighs as much as 2 fully loaded subway cars or an entire herd of 15 adult African elephants. And this is just one fragment of a giant construction set that will lock together hundreds of feet above the ground. Hidden inside each beam is an entire architecture. Diaphragms and stiffening ribs. These are internal steel walls that prevent the hollow box from collapsing under its own weight or wind pressure. They're welded inside every few yards, turning the beam into a super strong skeleton. On the surface of the beam sit massive steel ears or sockets. Steel cables supporting the glass roof covering will later be threaded through them. Each connection has to withstand tension of hundreds of tons, so welding them into the beam body is the most critical part of the job. A beam might be wider at the base and taper toward the edge, creating additional challenges when cutting the metal. This isn't mass production anymore. It's custom tailoring with 80-ton sheets of steel. When you look at a finished section at the Wisconsin factory, it seems like an immovable cliff. But engineers know better. Under its own weight, it'll sag slightly. That's why during fabrication, they build in what's called camber. They make the beam slightly curved upward so that after installation and loading, it becomes perfectly level. It's high-level math, where the weight of steel and the laws of gravity work together to create the Death Star's futuristic silhouette. The logistics operation of delivering Allegiant Stadium roof sections from Wisconsin to Nevada, this was a real roadshow stretching over 1,500 miles. When a steel beam of that weight rolls out the factory gates, it stops being just a component and becomes the king of the road, forcing traffic across entire states to bend around it. This wasn't your typical truck haul. Each beam required a specialized tractor-trailer combo, a super heavy-duty tractor, and a modular platform trailer whose axle count could reach 20 or more. This was done to distribute the massive weight of the metal without crushing the asphalt or collapsing bridges along the route. This whole monster, as long as half a football field, rolled onto the highway, taking up 2 lanes at once. The beam's width was so extreme that it extended far beyond the platform edges, essentially turning the truck into a moving wall. Every single trip was a special operation, choreographed down to the minute. Escort vehicles rode ahead and behind, strobes flashing. They measured bridge clearances with laser rangefinders in real time and coordinated freeway off-ramp closures. The toughest parts were turns and interchanges. The turning radius of a rig like this was so massive that the driver had to swing into oncoming lanes or even onto the shoulder, while specialized operators with remote controls separately steered the platform's rear axles to make the turn work. The process was complicated by the fact that these superloads were only allowed to move during daylight and in perfect weather. If high winds kicked up on the prairie or snowstorms hit in the mountains, the convoy would pull into special staging areas, waiting for a weather window. Speed rarely topped 30 miles per hour. This caravan crept across half the country, a massive black steel box rolling past Iowa cornfields or the red rocks of Utah. Drivers in oncoming cars slowed down, confused about what kind of piece of a spacecraft was heading straight toward them. This was an endurance test not just for the equipment, but for the nerves of the drivers hauling 80 tons of steel across continental America to the very heart of the gambling business. The assembly of Allegiant Stadium in Las Vegas became a real battle between the steel will of engineers and the merciless elements of the Mojave Desert. The main problem wasn't just the weight of the beams, but the extreme temperatures. When the sun heated the black steel to 158 degrees Fahrenheit, the metal physically expanded. This meant that a beam that fit perfectly into its slots in the morning could be several millimeters longer by afternoon, making connection impossible. That's why most of the critical lifts were done at night or in the pre-dawn hours when the metal calmed down. When the final bolt in the massive box beams was tightened, Allegiant Stadium finally got its completed steel skeleton. But it's the next phase that transformed this raw industrial structure into Nevada's architectural icon. The steel frame began getting dressed in glossy black wall panels and tinted glass, creating that seamless, monolithic look that earned the arena its Death Star nickname. Black in the desert, where the sun is relentless, seemed like a risky choice. However, the panels have a special coating that deflects a significant portion of thermal radiation. As the facades wrapped the metal, the stadium started resembling a massive spaceship that landed in the middle of the desert, or the sleek helmet of a Raiders player. Glass walls on the north side of the stadium, tall as a 10-story building, are retractable, opening up panoramic views of the glittering Las Vegas Strip, connecting the sterile comfort of the arena with the city's raw energy. The final price tag? $1.9 billion. That figure made Allegiant Stadium the most expensive stadium in the world when construction wrapped. Every cent of those billions shows up in the details, from lavish VIP suites to the massive Olympic torch honoring Al Davis inside. But the real value is hidden beneath those black panels. Those same beams from Wisconsin that traveled thousands of miles now support more than just a roof. They hold up Las Vegas's reputation as the world's new sports capital. When the stadium fires up its exterior lighting at night, the black metal becomes a canvas for millions of pixels, and the planet's priciest arena starts to glow, proving that the marriage of rough steel and high-tech can create something truly spectacular. Hold a 1-inch tungsten cube? It weighs nearly 1 pound, denser than gold, heavier than lead. Drop it and the floor dents, not the cube. This metal refuses to melt until 6,192 degrees, hotter than Earth's core beyond temperature where other metals vaporize. Light bulb filaments, armor-piercing bullets, rocket nozzles, tungsten survives conditions that destroy everything else. Yet it starts as dull gray rock, looking worthless. How does brittle ore transform into metal that won't surrender? Why does one nation control 70% of global supply? Stay with us. You'll witness industrial-scale mining reshaping mountains and discover tungsten's shocking secret. This indestructible metal is so brittle in pure form it shatters like glass. The Dayu tungsten mine in Jiangxi, China dominates the landscape. An open pit 3 miles across descending 800 feet into earth. Giant haul trucks, each carrying 400 tons, crawl spiral roads looking like toys from rim's edge. This single mine produces 40,000 tons of tungsten concentrate annually, enough to manufacture 2 billion light bulbs. 70% of world's tungsten comes from Chinese operations like this. Watch the blast sequence. Drillers bore holes 50 feet deep in geometric patterns across the pit floor. Each hole gets packed with explosives, 200 pounds per hole, hundreds of holes per blast. The detonation ripples across the face in sequence, fracturing 10,000 tons of rock in 30 seconds. Dust clouds billow 300 feet high, visible from orbit. What took nature millions of years to create, humans demolish in half a minute. The ore, wolframite and scheelite, contains just 0.5% tungsten. That means 99.5% is waste requiring removal. Massive crushers reduce boulders to gravel. Ball mills grind further. Rotating drums containing steel balls pulverize ore to powder finer than flour. The grinding noise is deafening, continuous thunder as metal crushes rock. Separation uses gravity and magnetism. Wolframite, being dense and magnetic, concentrates easily. Scheelite requires froth flotation. Chemicals make tungsten minerals hydrophobic, clinging to bubbles while waste sinks. The concentrate, now 15% tungsten, ships to processing plants. China's dominance isn't accidental. They control reserves, processing knowledge, and critically tolerate environmental damage Western nations won't accept. Tailings ponds stretch miles, filled with chemical-laced sludge that'll remain toxic for centuries. Processing concentrate into pure tungsten trioxide requires acid digestion. The concentrate gets dissolved in hydrochloric or nitric acid, violent chemical attack breaking molecular bonds. Tungsten dissolves while impurities precipitate out. The solution, now containing tungsten compounds, undergoes pH adjustment causing yellow tungsten trioxide powder to crystallize. This powder undergoes hydrogen reduction, the crucial transformation. Inside tube furnaces heated to 1,800 degrees, hydrogen gas flows over tungsten trioxide. The hydrogen strips oxygen atoms, leaving metallic tungsten powder. But here's the challenge. Pure tungsten powder is useless. The particles don't bond. Press them together and they crumble. Tungsten's ultra-high melting point makes conventional melting impossible. No crucible survives temperatures required. The solution? Powder metallurgy. Powder metallurgy bypasses melting through sintering. Particles fuse below melting point under pressure and heat. Tungsten powder gets pressed into desired shapes using hydraulic presses, generating 50,000 psi. The compacts, called green bodies, are fragile, handle roughly, and they disintegrate. The green bodies enter sintering furnaces operating at 4,500 degrees in hydrogen atmosphere. At these temperatures, tungsten atoms migrate across particle surfaces, welding together without liquefying. The process takes 12 hours. What emerges has transformed. The powder compact becomes solid metal with 99% density. Dimensional changes are predictable but significant. Parts shrink 18% during sintering. Engineers must design oversized greens compensating for this shrinkage. Pure tungsten remains problematic. It's brittle at room temperature, difficult to machine. The solution? Alloying. Adding 2% thorium or lanthanum dramatically improves workability. These elements prevent grain growth during sintering, creating fine-grained structure that machines more easily. The most common tungsten product worldwide is tungsten carbide. Tungsten powder mixed with carbon, sintered together. Tungsten carbide achieves hardness second only to diamond. Cutting tools made from tungsten carbide last 10 times longer than steel equivalents. Mining drill bits, machining inserts, industrial dies. Anywhere extreme wear occurs, tungsten carbide dominates. The material cuts steel like butter but shatters under impact. Drop tungsten carbide block on concrete and it explodes into fragments. The combination of extreme hardness and extreme brittleness defines tungsten's paradox. Wire drawing demonstrates tungsten's remarkable properties. The sintered tungsten gets heated to 3,000 degrees and drawn through progressively smaller diamond dies. The wire diameter reduces from 1/4 inch to thousandths of an inch, thinner than human hair for light bulb filaments. This drawing process work hardens tungsten, increasing strength. Modern LED lights made tungsten obsolete for household illumination, but specialty applications remain. Electron microscopes, X-ray tubes, high-temperature furnace elements. Anywhere electricity must flow through extreme heat, tungsten wire delivers. The element's resistance increases with temperature, making it self-regulating. In light bulbs, hot filament resists current flow, limiting power draw and preventing burnout from voltage spikes. That wire glowing white-hot at 6,000 degrees, tungsten operating at 70% of its melting point, yet lasting thousands of hours. Military applications drive demand relentlessly. Tungsten's density, 19.3 grams per cubic centimeter, nearly identical to gold, makes it ideal for kinetic penetrators. Armor-piercing ammunition uses tungsten or tungsten alloy cores. Fired from tank cannons at 5,000 feet per second, these projectiles punch through steel armor through sheer mass and velocity, not explosive force. The ethical controversy is intense. Depleted uranium performs similarly but raises radioactivity concerns. Tungsten offers equivalent performance without radiation, but mining's environmental cost is staggering. Each ton of tungsten requires processing 200 tons of ore, generating mountains of toxic waste. The metal that survives Earth's most extreme conditions is extracted through processes poisoning the planet. Swedish chemist Carl Scheele identified tungsten oxide in 1781, studying the mineral scheelite. Spanish brothers Juan and Fausto El Huyar isolated metallic tungsten 2 years later. The name derives from Swedish tungsten, heavy stone. For a century, tungsten remained laboratory curiosity. Everything changed when Thomas Edison needed light bulb filaments in 1879. He initially used carbon, which burned out quickly. By 1904, manufacturers switched to tungsten, revolutionizing electric lighting. World War I revealed tungsten's military value. High-speed steel cutting tools containing tungsten enabled mass production of weapons. Today's annual production exceeds 90,000 tons, with China dominating supply chains so completely that Western nations consider tungsten a strategic vulnerability. Carbon emissions remain problematic as tungsten production generates 8 tons of CO2 per ton of metal, primarily from energy-intensive processing. Recycling exists but remains limited. Only 30% of tungsten gets recycled, far below rates for aluminum or steel. Here's the secret we promised. Tungsten's incredible strength comes from its weakness. Pure tungsten is brittle, shattering easily. But that brittleness stems from its crystal structure. Atoms packed so tightly that dislocation movement, the mechanism allowing metals to deform, essentially stops. This atomic rigidity creates the highest melting point, extreme hardness, and resistance to deformation. The metal survives temperatures melting steel because its atoms simply refuse to move. Adding trace elements creates enough flexibility for workability while maintaining strength. From Chinese mountains to cutting edges worldwide, the transformation completes. We've mastered metal that defies conventional metallurgy, processing it through techniques developed when melting proved impossible. That drill bit cutting through rock, that filament glowing white-hot, that bullet-piercing armor, all share tungsten's fundamental contradiction. The strongest metal is also the most fragile. The element that won't melt is useless without powder metallurgy. We've learned to work with nature's extremes by accepting, not fighting, inherent limitations. Tungsten doesn't compromise. Neither do the engineers who've learned to shape it.
Every year, over 40 million new gadgets hit the market, but almost nobody knows about the metal that makes them actually work. Why can a tiny element buried deep underground literally launch an entire civilization, from the Bronze Age to modern electronics? And what do ancient swords, tin cans, and your smartphone have in common? In this video, we're uncovering the secret of tin, the metal that built the past, runs the present, and hides a fact you've definitely never heard before. Stick around until the end. That's where the real mystery reveals itself. Tin isn't just some new trend. This is a metal with a deep-rooted history spanning thousands of years. Its discovery sparked a genuine revolution that forever transformed the course of human civilization, launching what we call the Bronze Age. Picture this. Ancient craftsmen learned to extract copper and forge tools from it. But copper was soft. Then, whether by accident or experimentation, they discovered something remarkable. If you added a little bit of another then unknown metal to molten copper, tin, the alloy became incredibly strong, hard, easier to cast, and held a sharper edge. That metal was tin. The copper-tin alloy became known as bronze. Bronze swords, shields, tools, jewelry, all of this suddenly became accessible, giving ancient civilizations a massive advantage. It was a true technological leap that transformed warfare, agriculture, and art. Tin became so valuable that real battles were fought over its deposits, and trade routes to tin mines, like those in Cornwall, Britain, were incredibly important. Over the centuries, tin stayed valuable. It was used as a coating for other metals to protect them from corrosion. For example, tin plate, a thin sheet of steel coated with tin, which was used to make cans. It was also used to make soft solders that joined metals together, and in the production of mirrors, and even to create organ pipes and coins. But its true renaissance came in the 20th century with the rise of electronics. Over 50% of all global tin consumption goes to this industry. Solder. That's its main job. Your computer, smartphone, TV, inside them, thousands of electrical components are connected together. These connections are made using solder, which is usually an alloy of tin with other metals, like lead in the past, now mostly with copper, silver, or nickel. Tin is perfect for solder because it has a relatively low melting point, which makes it easy to melt and form connections without damaging sensitive electronic components. Tin also wets metals, meaning it easily flows across the surface, creating a strong electrical and mechanical bond. It's got great electrical conductivity too, and it's corrosion resistant.
Modern electronics use what's called lead-free solder, which is a huge step forward for the environment. Tin is the main component in these alloys. Without reliable soldered connections, the entire complex architecture of microchips would simply fall apart, and your gadget would turn into a pile of useless parts. Tin is used to coat other metals, especially copper, on printed circuit boards. This protects the copper traces from oxidation and makes the soldering process easier. It's also used to coat connectors, which improves their electrical conductivity and corrosion resistance. Tin isn't a super common element in the Earth's crust. Its primary mineral is cassiterite, basically tin oxide. It's a pretty dense mineral that's often found in placer deposits, meaning you can extract it from river sediments or ancient coastlines. Over 70% of the world's tin production is concentrated in 4 countries across Southeast Asia and South America: China, Indonesia, Myanmar, and Peru. This makes the tin market highly sensitive to political and economic events in these regions. Tin mining begins with the exploration phase. Geologists, armed with modern technology, conduct surveys, drilling, and analysis of soil and rock samples to find locations where cassiterite concentrations are high enough for economically viable extraction. Once a deposit is identified, development begins, which can follow 2 main paths depending on the type of deposit. The first and most common method of tin mining is from placer deposits. Picture this. Over millions of years, cassiterite washed from bedrock by water and erosion accumulated in riverbeds, at the bottom of lakes, or on ancient seashores.
It settled like sand in what's called placer deposits. Extracting from these deposits is often way simpler than digging underground mines. Here, they use massive dredges, floating factories that scoop up tons of soil and gravel from the bottom of waterways, or they deploy hydraulic monitors, powerful jets of water under high pressure that blast away soil from riverbanks or hillsides containing cassiterite. The blasted rock then flows to primary processing, where gravity methods, exploiting density differences, separate the cassiterite from lighter waste rock. Think industrial-scale gold panning, only gigantic. The second method? extracting from primary deposits, where cassiterite sits directly in solid rock. That's where traditional underground mines come in, same as mining any other metal. Miners drill tunnels and bore holes into the rock, use explosives to blast apart the ore vein, then loaders collect the ore and haul it to the surface. It's a more expensive and complex operation, requiring heavy-duty equipment and strict safety protocols. Once extracted, the ore, no matter where it came from, heads to a processing plant. First, it's crushed and ground into a very fine powder in mills to free the cassiterite crystals from the surrounding rock. Then various enrichment methods kick in. The first method, gravity separation. Since cassiterite is a pretty dense mineral, it gets separated from lighter minerals using water. This can happen in jigs, concentration tables, or spiral separators.
The second method is flotation. Sometimes, for further enrichment or to separate cassiterite from other minerals, flotation is used, where cassiterite selectively sticks to air bubbles and rises to the surface as foam. As a result of all these processes, a tin concentrate is obtained that already contains more than 50% cassiterite, or even more. This concentrate then goes to a metallurgical plant to produce pure metallic tin. Here, the concentrate, which is tin oxide, is mixed with coal, which acts as a reducing agent, and fluxes. Fluxes are substances that help separate impurities. This mixture is heated in special furnaces to high temperatures, typically around 2400 degrees Fahrenheit. At these temperatures, the carbon steals the oxygen from the tin oxide, releasing pure metallic tin, which melts and flows to the bottom of the furnace.
The molten crude tin still contains impurities from other metals, so it goes through another crucial stage, refining. This can be thermopurification, where the lead is heated to specific temperatures so other metals separate out or float to the surface. Or more often, electrolytic refining, which allows for extremely high tin purity. High purity means almost 100% in this case. Can you believe that? This is critically important, especially for the electronics industry, where even the tiniest impurities can affect conductivity and component reliability.
Hold titanium, strong as steel but 45% lighter. It won't rust, won't corrode, survives temperatures exceeding 3,000 degrees. Every Boeing 787 contains 32 tons of titanium. Your hip replacement? Titanium. The Mars rover wheels? Titanium. This metal starts as black sand on Florida beaches, transforms through chemistry so complex only a handful of facilities worldwide master it. In Henderson, Nevada, 40 miles from Las Vegas, TiMet operates America's largest titanium mill, a facility so critical to aerospace that government considers it strategic national asset. How does beach sand become jet engine parts costing $10,000 per pound? Why does titanium manufacturing require more electricity than small city consumes? Stay with us. You'll witness the violent beauty of molten titanium glowing like miniature sun and discover the shocking paradox. Titanium is Earth's 9th most abundant element, yet costs more than gold to produce. TiMet Henderson sprawls across 600 acres of Nevada desert, manufacturing complex visible from space. The main production building stretches half-mile long, housing forges that shake ground when operating. This single facility processes 15 million pounds of titanium annually, supplying 70% of Boeing's titanium needs plus Airbus, Lockheed Martin, medical device manufacturers worldwide. 800 workers operate around the clock, 3 shifts daily, never stopping. Watch the receiving area. Trucks arrive weekly from Gulf Coast processors carrying titanium sponge, porous metallic chunks resembling pumice stone, each batch representing 6 weeks of chemical processing. The sponge, shipped in argon-filled containers preventing oxidation, gets immediately transferred to sealed storage. Titanium's reactivity demands constant vigilance. Expose hot titanium to air and it burns spontaneously, unquenchable. The entire facility operates under strict protocols. No sparks, no contamination, no mistakes. One error could destroy million-dollar equipment and kill workers. The vacuum arc remelting furnace is where titanium is reborn. This massive chamber, 20 feet tall and 6 feet diameter, operates in complete vacuum. Any oxygen presence causes catastrophic contamination. Workers load titanium sponge mixed with scrap recycle into electrode molds, creating consumable electrodes weighing 6 tons each. The furnace chamber gets evacuated to 0.001 atmospheres, essentially space-level vacuum. Electric arc strikes between electrode and water-cooled copper hearth. The current, 20,000 amps at 40 volts, melts titanium at 6,300 degrees. Molten droplets fall into ingot mold below, solidifying layer by layer. The process takes 18 hours per ingot, consuming enough electricity to power 400 homes daily. Watch through observation port as titanium glows white-hot, brighter than welding arc. The light carries ultraviolet radiation. Direct viewing causes instant eye damage. The ingot emerging weighs 12,000 pounds, purity exceeding 99.9%. The cogging press transforms ingots into workable forms through brute force. This hydraulic press generates 14,000 tons of pressure, equivalent to stacking 7,000 cars on single point. The titanium ingot, reheated to 1,800 degrees in induction furnace, glows orange when positioned under press. Operators work from shielded control room, manipulating ingot via robotic arms. The press descends with earth-shaking impact. Each strike reduces ingot thickness by inches while increasing length. The titanium screams, metallic shriek as crystal structure deforms under impossible pressure. Workers rotate ingot 90 degrees between strikes, ensuring uniform reduction. The process requires 48 heating cycles and 200 press strikes over 12 hours. What was cylindrical ingot becomes rectangular billet suitable for rolling. The precision is remarkable despite violence. Dimensional tolerances remain within 0.05 inches across 20-foot length. Hot rolling mills shape titanium into plates, bars, and sheets. The billet, maintained at 1,700 degrees, passes through series of roller stands, each applying progressively greater reduction. The rollers themselves, made from high-speed tool steel, wear out monthly despite water cooling. Titanium's abrasiveness destroys ordinary metals. The mill building vibrates continuously, low-frequency rumble felt in bones rather than heard. Watch the titanium emerge, glowing ribbon extending at 15 feet per second. Scale: titanium oxide forming on surface, flakes away in showers of sparks. Workers monitor thickness using laser micrometers accurate to thousandths of inch. Any deviation triggers automatic adjustment. The plate exits at quarter-inch thickness, cooled via air blast to 800 degrees before transfer to finishing area. This single rolling operation produces material worth $2 million per batch. Precision machining happens in climate-controlled clean rooms where temperature varies less than 2 degrees. Titanium's properties, low thermal conductivity, high strength, make it notoriously difficult to machine. Cutting tools overheat rapidly, dulling within minutes. The facility uses carbide-tipped tools cooled by pressurized coolant flowing at 50 gallons per minute. Each Boeing 787 wing spar requires 200 hours machining from solid titanium billet. CNC mills operate continuously, removing 80% of material as chips. These chips, valuable as raw material, get collected for recycling. The machining bay contains 40 CNC mills, each costing $3 million. Operators monitor multiple machines simultaneously, changing tools and verifying dimensions. A single programming error could destroy part worth $100,000. The facility maintains zero defect requirement. Aerospace applications tolerate no margin for error. Parts get triple inspected using coordinate measuring machines, accurate to millionths of inch. Quality control involves destructive and non-destructive testing. Ultrasonic inspection sends sound waves through titanium, detecting internal defects invisible to naked eye. Voids, cracks, inclusions, any imperfection appears on computer screen. X-ray fluorescence verifies chemical composition, ensuring no contamination from iron, carbon, or other elements degrading properties. Sample coupons get pulled from each batch for tensile testing. Hydraulic machines pulling specimens until they break, measuring ultimate strength. The testing laboratory maintains records on every ingot produced since 1950. Each piece of titanium carries pedigree, chemical analysis, mechanical properties, processing history, traced from beach sand through final product. This documentation follows material through entire supply chain. When aircraft manufacturer receives titanium part, complete history accompanies it. The traceability isn't bureaucracy, it's survival. Component failure at altitude kills people. The quality system prevents that. Timet's Henderson facility began operation in 1951 as Titanium Metals Corporation of America. Cold War drove expansion. Military aircraft demanded titanium for speed and performance. The SR-71 Blackbird contained 93% titanium by weight, enabling Mach 3+ speeds. Commercial aviation adopted titanium in 1960s as Boeing 747 entered service. Medical applications emerged in 70s when surgeons discovered titanium's biocompatibility. Human bone fuses directly to titanium implants. The Henderson plant survived industry consolidation, multiple ownership changes, bankruptcy restructurings. In 2023, Precision Castparts acquired TIMT, integrating it into aerospace supply chain. Today's facility bears little resemblance to 1950s operation. Automation replaced manual labor. Computer control optimized processes. But core challenge remains unchanged. Transforming reactive metal into reliable material requires uncompromising precision and perpetual vigilance. Environmental impact seems paradoxical. Producing titanium generates significant carbon emissions, mainly from electricity consumption during vacuum melting. The Henderson facility uses 500 million kilowatt-hours annually, equivalent to 50,000 homes. Yet titanium's properties enable lighter aircraft burning 30% less fuel over lifetime. A single Boeing 787 using titanium structure prevents emission of 1 million tons CO2 versus aluminum equivalent over 30-year service life. Here's the secret we promised. Titanium is absurdly abundant, Earth's 9th most common element, yet harder to produce than platinum. The metal's extreme reactivity means it cannot be smelted like iron or copper. Traditional metallurgy fails completely. The Kroll process, vacuum arc remelting titanium sponge, remains only viable production method despite being invented in 1940. We're using 75-year-old technology because nothing better exists. Every attempt to improve efficiency fails against titanium's fundamental chemistry. From Nevada desert to Boeing assembly lines worldwide, the transformation completes. Time at Henderson represents industrial capability few nations possess. The knowledge, infrastructure, and precision required to master titanium. That jet carrying you across oceans depends on metal processed in this desert facility. The hip implant restoring mobility came from Henderson furnaces. We've built aerospace dominance on metal that fought us every step, that demanded we develop entirely new manufacturing processes, that costs fortune to produce despite natural abundance. Titanium doesn't compromise. Neither does Henderson. The facility runs continuously, glowing furnaces melting metal that makes modern aviation possible. Stand at Ground Zero, New York City. One World Trade Center rises 1,776 feet. Deliberate height honoring Independence Year. This building contains promise. It will never fall again. That promise lives in 45,000 tons of structural steel and 200,000 cubic yards of concrete. But concrete alone crumbles under stress. What gives it strength are 300 million pounds of steel rebar, ribbed bars running through every column, every beam, every floor. Each bar began as scrap metal melted at 3,000 degrees, rolled into ribbed shape, cut to exact length, trucked from South Carolina mill to Manhattan, and positioned with surgical precision. How does junked car become foundation of America's safest building? Why does rebar require ribs instead of staying smooth? Stay with us. You'll witness electric arc furnace creating artificial lightning and discover rebar's critical secret. Those ribs aren't decoration, they're mechanical bond preventing concrete from tearing itself apart. Nucor Steel Berkeley in South Carolina produced most rebar for One World Trade Center. This facility processes 2 million tons of scrap steel annually, and enough to build 12 Empire State Buildings yearly. The scrapyard stretches quarter-mile. Mountains of crushed cars, demolished buildings, retired appliances, old rebar from previous demolitions. Giant electromagnets lift entire automobiles, dropping them into sorting lines separating steel grades. Every day, 600 trucks deliver scrap. Every day, 400 trucks leave carrying finished rebar. Walk the scrap processing area. Shredders pulverize cars in 8 seconds. Same time it takes to read this sentence. Hydraulic shears cut structural beams like scissors through paper. The noise is relentless. Metal tearing metal, magnets clanging, conveyor belts grinding. One supervisor explains, "We see America's past arriving daily. Cars people drove to work, buildings where they lived, bridges they crossed. We melt history and rebuild tomorrow." For World Trade Center project, this facility operated 24/7 for 3 years straight, producing 3,000 tons monthly, enough rebar to circle Manhattan Island 40 times. The electric arc furnace transforms scrap into liquid steel through controlled lightning. This vessel, 40 feet diameter and 30 feet deep, contains 3 graphite electrodes 2 feet thick descending from roof. When 90 megawatts flow power for 70,000 homes, arcs jump between electrodes and scrap, generating 5,800 degrees. The scrap melts in minutes. Watch through protective glass as metal liquefies, glowing white hot then orange as temperature stabilizes. 200 tons of scrap loads per batch. The electrodes pierce the pile, current flows and artificial lightning strikes continuously. The sound resembles continuous thunder. The heat radiates through observation room despite water-cooled walls. Oxygen lances inject pure oxygen at supersonic speeds, burning impurities. Carbon oxidizes to gas, sulfur evaporates. Phosphorus combines with lime-forming slag that floats atop molten steel. Temperature control is absolute. Too hot wastes energy, too cool leaves impurities. Computer systems adjust power and oxygen flow thousands of times per melt, maintaining exact chemistry required for construction-grade rebar. Tapping releases 200 tons of liquid steel into ladle, refractory-lined bucket mounted on railcar. The pour takes 8 minutes, continuous stream of glowing metal creating updrafts lifting dust into air. Workers monitor from shielded stations, faces illuminated by orange glow. The steel, now 3,050 degrees, travels to continuous caster where transformation into solid bar begins. The caster pours molten steel into water-cooled copper mold, oscillating rapidly. As steel contacts mold, outer shell solidifies while interior remains liquid. The strand, continuous ribbon of solid steel, emerges from bottom, bent gradually from vertical to horizontal through roller system. Torches cut the continuous strand into billets 20 feet long, each weighing 4 tons. These billets, still glowing red at 1,800 degrees, feed directly into rolling mill. The entire process from scrap to billet takes 90 minutes. For WTC project, Berkeley ran 3 melts daily, producing 18,000 tons monthly during peak construction. The rolling mill transforms square billets into ribbed rebar through precision violence. The billet enters roughing stand where rollers squeeze and elongate it, reducing thickness while increasing length. Each pass through successive roller stands further reduces diameter. The steel, maintained at 1,600 degrees, glows orange-red, extending like taffy under roller pressure. 22 passes transform 4-ton billet into 500 feet of rebar. But here's where rebar gets its identity, the ribs. Special roller dies emboss transverse ribs and longitudinal ridges onto surface. These aren't decorative. The ribs increase surface area by 40%, creating mechanical bond with concrete. Smooth bar would slip under stress. Concrete would crack and fail. Ribbed bar locks into concrete through friction and mechanical interlock. The rib pattern follows precise standards. Height, spacing, angle, all controlled to thousandths of inch. For WTC, specifications demanded grade 75 steel, yielding at 75,000 psi, 3 times stronger than standard residential rebar. After rolling, the rebar, still 800 degrees, enters cooling bed where water jets control cooling rate. Fast cooling creates hard but brittle steel. Slow cooling produces soft but weak steel. Controlled cooling achieves optimal balance. Computer systems adjust water flow based on bar diameter, steel grade, ambient temperature. The bars cool from orange to black in minutes, steam rising in clouds. Then comes straightening. The hot rolling process introduces slight curves. Straightening machines grab bars between sets of rollers positioned at angles, pulling and pushing until perfectly straight. Deviation under 0.01 inches per 40 feet. Next, shearing machines cut bars to exact lengths. For WTC, typical lengths were 40 and 60 feet, sized to fit concrete forms with minimal waste. Flying shears cut moving rebar at speeds exceeding 20 feet per second. The cut must be square, clean, burr-free. Each bar gets stamped with grade marking and mill identification. Quality control happens continuously. Samples from every heat, every batch of melted steel undergo testing. Tensile machines pull specimens until they break, measuring yield strength, ultimate strength, elongation. Chemical analysis verifies carbon, manganese, silicon content. Dimensional inspection confirms rib height, spacing, and bar diameter. Every bar carries traceability, heat number linking it to specific melt, specific chemistry, specific mechanical properties. For one World Trade Center project, quality standards exceeded normal construction. The Port Authority required additional certifications, independent testing, complete documentation. Rejected bars got remelted. No shortcuts existed. One quality inspector recalls, "Every bar we shipped could end up in critical structural element. We tested knowing thousands of lives would depend on our work being perfect." The facility maintained 99.8% acceptance rate, meaning just 2 bars per 1,000 required remelting. Rebar's invention dates to 1850s France, when Joseph Monnier, a gardener, reinforced concrete flower pots with iron mesh. He discovered concrete's compression strength, combined with iron's tensile strength, created superior material. By 1900s, rebar became standard in construction. The ribbed surface pattern emerged in 1930s after engineers realized smooth bars failed under dynamic loading. Earthquakes, wind, vibration caused concrete to slip along smooth bars. One World Trade Center's foundation began in 2006. Final steel placed in 2012. During construction, 600 trucks daily delivered materials to Manhattan site. Rebar arrived on flatbed trucks, each carrying 25 tons, 40 to 50 bars per load. Cranes lifted bundles to specific floors where iron workers tied bars into 3-dimensional cages matching structural drawings. For the concrete core building's spine, rebar spacing was 4 inches on center in both directions, creating steel mesh so dense you could barely see through it. Environmental impact shows interesting paradox. Producing rebar from recycled scrap uses 60% less energy than making steel from iron ore. Berkeley facility prevented mining 200,000 tons of iron ore annually. Yet steelmaking remains carbon intensive. Melting metal requires massive electricity. Each ton of rebar generates 1.8 tons CO2 emissions. For WTC's 300 million pounds, that meant 270,000 tons CO2, equivalent to annual emissions from 30,000 cars. Here's the secret we promised. Rebar ribs create mechanical bond, but their real genius is crack control. Concrete always cracks. Thermal expansion, settling, loading all cause microscopic fractures. Smooth rebar allows cracks to propagate, widening until failure. Ribbed rebar intercepts cracks, distributing stress across multiple ribs, preventing single crack from becoming catastrophic failure. Those ribs transform concrete from brittle material into ductile system that bends before breaking. At WTC, this matters profoundly. The building must survive impacts, explosions, earthquakes that would destroy conventional structures. From South Carolina scrapyard to Freedom Tower rising above Manhattan, the transformation completes. Nucor Berkeley melted America's discarded metal and reformed it into symbol of resilience. That rebar, 300 million pounds of it, creates skeletons stronger than original towers. Every bar positioned perfectly, every connection inspected, every pore documented. The building stands because thousands of workers understood. This isn't just construction, it's promise. Promise that engineering will triumph over terror, that steel and concrete and human determination can create something genuinely unbreakable. Those ribs running through every column aren't just preventing concrete failure, they're preventing failure of a different kind. The failure to rebuild, to remember, to rise again. Board, New York City subway, 5.5 million people daily. You grab the pole, doors close, train accelerates into darkness. The car carrying you weighs 85,000 pounds, contains 20 miles of electrical wiring, 10,000 individual components, and required 6 months to build. This 60-foot steel box began as flat sheets in Nebraska cornfields, traveled through 2 factories across 1,200 miles, and survived testing that would destroy ordinary vehicles. One company builds every new NYC subway car, Kawasaki, operating facilities in Lincoln, Nebraska, and Yonkers, New York. How does 40 tons of steel become underground transportation for millions? Why does single subway car cost $3 million? Stay with us. You'll witness welding robots joining steel with surgical precision and discover Subway's shocking secret: the air hockey floor that lets 2 workers move 85,000-pound train car by hand. Kawasaki Motors Manufacturing in Lincoln, Nebraska occupies 733,000 square feet. Facility so large you could fit 12 football fields inside. This plant produces subway cars for New York, Washington, D.C., and other major cities. For NYC's R211 order, Lincoln operates 3 dedicated production lines running 24/7. The facility manufactures 22 cars monthly, 1 complete subway car every 33 hours. Walk the receiving dock where flatbed trucks deliver stainless steel sheets from ArcelorMittal and Nucor mills. Each sheet measures 12 feet by 40 feet, weighs 800 pounds. One subway car requires 50 steel sheets totaling 40 tons. The factory floor operates on technology found nowhere else in North America: air bearing system. The entire floor contains thousands of tiny holes releasing compressed air, creating cushion between floor and work platforms. Each 85,000-pound subway car sits on platform floating on air film thinner than credit card. 2 workers can push entire car anywhere in facility. The floor stays so flat, tolerances within thousandths of inch that it resembles polished mirror. This system provides ultimate manufacturing flexibility, allowing cars to move between workstations without tracks or cranes. Car body construction begins with laser cutting. German-made Trumpf laser cutters slice stainless steel with 15,000-watt beams, cutting through half-inch steel at 30 inches per minute. The laser follows computer patterns precise to 0.005 inches. Side panels, roof sections, floor plates, end walls. Every piece cut to exact dimensions. Burrs get removed through automated deburring stations. The steel, grade 304 stainless, contains 18% chromium and 8% nickel, providing corrosion resistance for 40-year service life in humid subway tunnels. Welding robots join the pieces. 6 Kawasaki-built robots work simultaneously on single car, each programmed for specific welds. MIG welding, metal inert gas, uses argon shielding preventing oxidation. The robots lay 3,000 linear feet of weld per car, moving at precisely controlled speeds. Watch robotic arm trace floor-to-wall joint. The weld bead forms perfectly uniform, penetrating through both pieces, creating joints stronger than base metal. Welders wearing auto-darkening helmets monitor every joint. One supervisor explains, "Robot makes perfect weld every time, but human checks every inch. We're building transportation for 5 million people daily." The car shell, bare steel skeleton, moves to assembly station where floor installation begins. Plywood subflooring goes down first, providing sound dampening and thermal insulation. Over this, workers install rubber flooring material designed for subway service. Slip-resistant, easy to clean, resistant to chemicals and fluids. The flooring attaches via adhesive and mechanical fasteners every 6 inches. Ceiling panels install next. White fiberglass reinforced plastic reflecting LED lighting. These panels contain 16 air conditioning vents per car, each precisely positioned for optimal airflow. Interior wall panels get mounted to steel framework. Each panel, formed from molded fiberglass, fits specific location. The panels interlock via hidden fasteners, creating smooth interior surface. Behind walls, workers route conduit for electrical systems. Every wire, every cable follows engineering drawings, specifying exact paths. The conduit protects wiring from vibration, moisture, and passenger contact. Installing interior panels on single car takes 12 workers 3 days, 96 man-hours of precision fitting. Electrical installation is where complexity peaks. Each R211 car contains 20 miles of wiring, enough to stretch from Lincoln Factory to downtown Omaha. 3 master electricians and 6 assistants spend 2 weeks per car running wire. The wiring includes power distribution, lighting circuits, door controls, HVAC systems, communication systems, passenger information displays, and CBTC, communication-based train control. Every wire gets labeled at both ends with alphanumeric codes. Color coding follows strict standards: red for positive power, black for negative, green for ground, yellow for control signals. The main electrical cabinet, brain of the car, occupies space beneath seating. This cabinet contains 70 circuit breakers, 40 relays, 12 transformers, and computer control modules. Workers connect each wire to specific terminals, torquing every connection to exact specification. 25 inch-pounds prevents loose connections causing failures. Testing happens continuously. Multimeters verify every circuit. Megohmmeter tests insulation resistance. Must exceed 100 megohms between any circuit and car body. One electrical error could disable entire trains, so triple checking is standard procedure. Door installation requires watchmaker precision despite massive scale. Each car has 4 door sets, 8 individual panels. The doors, 58 inches wide, are 8 inches wider than previous generations, reducing station dwell time by 30%. Each door weighs 200 pounds, hangs on aircraft-grade bearings rated for 10 million cycles. Pneumatic actuators powered by 100 psi compressed air open and close doors in 2 seconds. The door edges contain rubber seals preventing finger injuries. LED strips around each door flash green when opening, red when closing. These lights contain 500 individual LEDs per car, controlled by dedicated microprocessor. Seating installation follows specific layout. Blue molded fiberglass seats designed for durability and easy cleaning. Yellow flip seats provide wheelchair space. Grab poles, stanchions, and handrails installed according to accessibility standards. The looped stanchions, unique design allowing multiple grip points, get welded to floor and ceiling, tested to withstand 500-pound side load. Digital displays mount above doors. 28 screens per car showing route information, station stops, and service alerts. Each screen connects via Ethernet network running entire train length. After 8 weeks in Lincoln, the car, still incomplete, loads onto flatbed truck for 1,200-mile journey to Yonkers, New York. Multiple cars ship weekly on specialized railcar transport trucks. The Yonkers facility, 250,000 square feet, occupies former Otis Elevator Factory. Here, final assembly transforms Lincoln-built shells into operational subway cars. The facility maintains quarter-mile test track, elevated rails allowing full-speed testing indoors. Workers install propulsion systems. Alstom-built Optonix traction motors, generating enough power to accelerate 85,000-pound car from 0 to 50 miles per hour in 30 seconds. 4 motors per car, each weighing 1,200 pounds. The motors connect to trucks, wheel assemblies containing suspension, brakes, and gearing. Brake systems use both pneumatic and electrical braking. Pneumatic provides emergency stopping. Electrical regenerative braking converts motion energy back to electricity, feeding power line. Installing and aligning propulsion system takes 5-person crew 1 week per car. Testing begins before car leaves factory. Static tests verify all electrical systems function correctly. Doors cycle 1,000 times. HVAC runs continuously for 48 hours. Every light, every display, every sensor gets checked. Then dynamic testing, the car runs on indoor test track, accelerating, braking, taking curves at speed. Computers monitor bearing temperatures, wheel alignment, electrical consumption, brake performance. The test track includes curve equivalent to sharpest turn in NYC subway system. Track engineers verify car navigates without derailment risk. 5 car sets get assembled and tested as complete trains. The open gangway R211T models, 20 cars featuring accordion connections allowing passengers to walk between cars, undergo additional flex testing. Workers measure gangway movement through curves, verifying seals maintain integrity. Sound testing measures interior noise levels. Must stay below 85 decibels at speed. Climate testing runs HVAC at temperature extremes. After passing all tests, the train gets final inspection. MTA representatives examine every detail before acceptance. Rejection rate runs 2%. Rejected cars return for correction, delaying delivery. Kawasaki entered U.S. railcar manufacturing in 1982, winning contract for NYC's R62 subway cars. Since then, the company delivered over 5,000 railcars to American transit agencies. The Lincoln facility opened in 2001 specifically for subway car production, utilizing techniques developed building Japanese Shinkansen bullet trains. The Yonkers plant, established in 1986, has produced cars for every major northeastern transit system. Completed R211 cars travel final miles to New York City via their own power or rail transport, arriving at Coney Island Yard or Pitkin Yard for 30-day acceptance testing. Transit workers operate cars on actual subway lines during non-revenue hours, monitoring performance. After successful testing, cars enter passenger service. The first R211A cars began service March 2023 on the A train. Open gangway R211Ts entered service February 2024 on the C line. Eventually, 1,610 R211 cars will replace entire fleets of R46 and R68 cars built in 1970s. Environmental impact shows interesting contradiction. Manufacturing subway car generates approximately 40 tons CO2 emissions, mostly from steel production and electricity consumption. However, one car serving 40-year life transports 100 million passengers, preventing equivalent of 20 million car trips. Net carbon savings exceed 10,000 tons CO2 per car over lifetime. The stainless steel body is 95% recyclable. After 4 decades service, retired cars get shredded, steel returns to mills, becomes new cars. Here's the secret we promised. Subway cars' 40-year lifespan means it outlasts almost everything else humans build. Your car lasts 15 years, your phone lasts 3. But subway car manufactured today will still be carrying passengers in 2065. That's why single car costs $3 million, because every component must survive 40 years of daily violence. Doors opening and closing 50 times per trip, 400 trips daily, 6 million cycles over lifetime. Electrical systems enduring temperature swings from freezing to 100 degrees. Structural steel flexing through millions of acceleration and braking cycles. The engineering isn't just about building strong car. It's building car that stays strong through 4 decades of punishment that would destroy normal vehicles in months. From Nebraska cornfields to Manhattan tunnels, the transformation completes in 6 months. Kawasaki's Lincoln and Yonkers plants represent capability concentration, decades of railcar knowledge, specialized equipment found nowhere else, and workforce expertise impossible to replicate quickly. That R211 carrying you through subway system contains work of 300 workers across 2 states in 6 months. Those 20 miles of wiring, 10,000 components, 3,000 feet of welds, all positioned perfectly, all tested thoroughly, all guaranteed to function for 40 years. You board, you ride, you exit, never thinking about the engineering miracle carrying you. But now you know, nothing about subway car is simple. Everything is deliberate, tested, and built to outlast almost everything else in your life.